We have started to deal with the problem of longitudinal vibration of air columns in our previous lecture. And you have seen in the first part of the lecture on this vibration of air columns, we have only derived the equation of motion. And the final equation of motion was just the classical wave equation. But as I have told you earlier, that in this chapter our aim is not to deal with the wave aspect. We only consider the vibration or oscillation. Okay. I have told you that actually a gaseous column behaves just as a continuous medium, because at ordinary pressure there is a large number of molecules in a small volume of the gas, and so that the average distance between the molecules is very small, and so it can be approximated to just as a continuous medium. And you have seen in this first figure I have considered a tube of uniform cross section filled with air or gas, and it is in undisturbed condition, which is called equilibrium state. In this condition, actually, if you divide the air column into elementary elements or slices, then you find the equation of motion by applying a disturbance on this system. Okay. So these two figures I have already discussed in the previous lecture for obtaining the equation of motion. But our prime aim in this case too is to find the frequencies and the shapes of the normal modes of vibration. So how we can actually find the frequencies and the shapes of the normal modes of vibration in this case? Today we are going to see this problem. Okay. And so having deduced the equation of motion of the particles of the gas, we can now obtain the possible normal modes of longitudinal vibrations of the column of gas under specified boundary conditions. You will see later on we will consider actually two cases. Okay. The first case will be our tube is open at one end and closed at other end. And in the second case, we will consider a tube which is open at both ends. Actually, when this problem will be dealt in case of waves, particularly in sound waves, then the first kind of tube which is closed at one of its ends, that is called actually a closed organ pipe. And when you talk about a tube which is open at both of its ends, that is called open organ pipe. Okay. But here our aim is not to discuss the wave aspect, only the vibration of the air column. Okay. Now we consider actually that as you have seen earlier, that there exists a normal mode of angular frequency omega and a phase constant phi. Actually, when you say that there exists a normal mode at frequency omega and phase constant phi, what does it mean? Actually, it means that every particle of the gas column executes simple harmonic motion of angular frequency omega and phase constant phi. But here the amplitude of the SHM for different particles will be different. That will depend on position. So as we have assumed the oscillation of the particle along the x-axis, so you can say that the amplitude of oscillation will be a function of x. Okay. And therefore, if you consider at any moment t the displacement of the oscillating particle denoted by the symbol y of xt, what will be that? That will be just represented by the equation of SHM. And you know, equation of SHM is given as 8 times cosine of omega t plus phi, or 8 times sine of omega t plus phi, or in exponential form. Here I have used cosine function, but instead of this cosine function you may use sine function. Okay. So the displacement of a particle of of this gas at any moment t at position x is given as a of x times cosine of omega t plus phi. Here, as you know, this a of x is the amplitude of oscillation which depends on x. Okay. Now actually for finding, you have seen in the previous lecture, what is the equation of motion of the gas element. So I have written here that the final result directly because you have already learned this thing in my previous video. So you have seen that the equation of motion of the element of gas is given as del 2y by del t square equal to v square times del 2y by del x square, where you know this v is a constant here. Actually, when you see this equation, definitely you have a concept in your mind that this is nothing. This is simply the differential equation of a wave or the classical wave equation. In case of wave, you know this v represents the phase velocity of the wave, but here we will say that this v is only a constant. And you have seen in my previous video that this v actually depends on two factors. One is the elasticity of the medium and another is the density of the medium. Actually, in my first video, I have written the bulk modulus of elasticity by the symbol B. But here I am writing the symbol E due to some reason. Because you will see later on in our calculation, we will use the symbol B for a constant, that is for the integration constant in solving the differential equation. So I have replaced this symbol B by E, but meaning is same. Here you can say that this E stands for the bulk modulus of the gas, okay, and rho is its density. Now our aim is to find these two partial derivatives, that is del 2y by del t square and del 2y by del x square from this equation 1. And after getting the values of these second order partial derivatives of y with respect to t and x, we will substitute those values in this equation 2 to get the required result. Okay. So let us try to find these two partial derivatives from this equation 1. It is very easy. You can easily find it. As you can see, if you will differentiate this y 2 times with respect to x partially, keeping t constant, then this cosine of omega t plus phi, this factor will be treated as a constant. Only this a of x will be differentiated. Since a is only a function of x, it is independent of t. Therefore, I have written d2a of x by dx square, not del 2ax by del x square, because in case of a function which is a function of only one variable, there is no difference between the partial derivative and its ordinary derivative. So I have written ordinary derivative d2a of x by dx square times this much. Okay. Similarly, when you will differentiate this y 2 times with respect to t partially, you will have to keep this ax as a constant factor, and this cosine function will get differentiated 2 times. So after differentiation, we get del 2y by del t square equal to minus omega square times ax times cosine of omega t plus phi. Okay. Now after getting these two partial derivatives, let us substitute them into this equation, in this equation number 2. Okay. So instead of del 2y by del t square, now you have to write this much, and instead of this del 2y by del x square, you should write this much. Okay. So let us substitute it. Now you can see this will be minus omega square ax times cosine of omega t plus phi, and that's equal to v square times d2 ax by dx square times cosine of omega t plus phi. Okay. Now you can see this cosine function in both sides will cancel out. Okay. And therefore, when you will simplify this result, you will get d2a of x by dx square equal to this much. This is minus omega square over v square times ax. Okay. And when you will bring this term in RHS, in LHS, this will become plus, and instead of omega square over v square, I have written k square. Okay. So our result is d2a by dx square plus k square a equal to 0, where k has been written instead of omega over v. Again, I will like to tell you that this k, when you will study the wave motion, this k will be recognized as wave vector or the wave number, which is actually a most important characteristic of a wave. But here, for the time being, I will not call it wave vector because we are not talking about any wave. So here I will only say that this k, which is equal to omega over v, that is a constant. Okay. Now see this equation. This equation has the same form as that of the equation of SHM. You know, equation of SHM is d2x by dt square plus omega square x equal to 0. So the form of both of these two equations you can see are same. So this is just the equation of SHM in space, not in time. Here we can say that the function A is oscillating with respect to space, not with respect to time. So since the form of this equation is same, so definitely its solution will be exactly same as that of the general solution of a simple harmonic motion. Only we have to replace the variable t in the solution of equation of SHM by x. Okay. So the general solution of this equation 3 can be written as a of x equal to a sine kx plus b cos kx, because you write the solution of this equation as a sine omega t plus b cos omega t. Here at the place of omega there is k, and at the place of t there is x. Okay. So in this way we have obtained the amplitude a of x. Okay. Actually in this expression, this a and this b are integration constant, since it is a differential equation of second order. So definitely when you will actually solve it, you have to integrate it 2 times. And during those 2 integration, you will have to use 2 integration constant. Actually, these a and b are those integration constants. Okay. And you know, whenever we have to find the actual value of the integration constant in a particular physical problem, definitely we must have some boundary conditions. And using those appropriate boundary conditions, we are able to find these constants. So in this case too, we will try to find these constants by using the appropriate boundary conditions. Okay. Now, after getting the value of a of x as a function of x, now let us substitute this value of a of x in this expression for displacement, that is y of xt. Instead of a of x, now put that value which you have obtained. So you can see this y of xt is now given as a times sine kx plus b times cos kx times cos omega t plus phi. Okay. Now, actually, when you talk about the vibration of a column of air or gas, Actually, you have seen in my previous video that in this case there is a variation in pressure of the medium. Okay, pressure of the medium does not remain at its equilibrium value, but it changes, and that pressure variation, which is also called excess pressure, that actually oscillates. So now we are going to change the displacement variation in terms of the pressure variation. But how we can do it? For this, you have to remember a, an important result of our previous lecture. You have seen that in the previous lecture we have obtained the value of the excess pressure, that is the change in pressure, which is denoted by the symbol delta P, and this is actually equal to bulk modulus times strain. Actually, this delta P here, which is excess pressure, that is just equivalent to bulk stress. Okay, and del y by del x, you have seen in my previous video, this is nothing, this is simply the bulk strain. Okay, so when you will find the bulk modulus of elasticity E, this will be a stress divided by strain. Okay, but as I have told you in my previous video that here this minus sign is required for getting the positive value of elasticity. So you have seen earlier that this delta P is given as minus E times del y by del x. Okay. Now if you want to find the value of this delta P, then you must have to find the value of this del y by del x. How this del y by del x we can get? You can get the value of del y by del x from this equation 5. For this you have to differentiate this y partially with respect to x, because y is also a function of t. So when we will differentiate it partially with respect to x, what will be our result? This will be simply equal to k times a cos kx minus b sin kx times this much, cosine of omega t plus phi. Okay. Now let us put this value of del y by del x here in the expression for delta P. And when you will substitute it, you can see this delta P will be equal to k times E times this much. Here I have actually taken minus sign as a common factor, that is minus 1 as a common factor, so this minus minus will become plus. So delta P, finally we get this is k times E times b sin kx minus a cos kx and multiplied by this cosine of omega t plus pi. Okay. Now after getting the value of this excess pressure, now we shall determine the frequencies and the shapes of the normal modes of longitudinal vibrations of column of a gas enclosed in a tube under the two important boundary conditions. So as I have told you earlier that we will consider actually two situations or two cases. In the first case, we are going to see what will be the normal mode frequencies and shapes when the tube is closed at one end and open at the other. And as I have told you earlier that in case of sound wave, when we will study the same problem, that propagation of sound wave in a tube, in an air column, then we will consider actually closed organ pipe and open organ pipe. So this is actually the case of closed organ pipe. Okay. When you say closed organ pipe, what does it mean? It means there is a tube filled with air or any gas, and this tube is closed at one end and open at the other end. So I have shown here that there is a tube of length L and it is lying along the x-axis, and its end at x equal to 0 is open, and its another end which is at x equal to L, that is actually closed. Okay. So the end x equal to 0, which is open, and x equal to L, which is actually closed, we have considered it. Okay. Now, as you know that an open end represents a condition of zero pressure variation. So when you talk about the pressure variation at this end, there will be no pressure variation because this is open end. And since there will be no pressure variation here, actually the you may say, if you compare this problem with the problem of a rod, this is the end of the rod which is not clamped. So the particles at this open end are completely free and it move with maximum displacement. Okay. So actually from this idea you can also say that the particles at the open end are under no strain. No strain is developed at the open end. And if no strain is developed, then stress will be also zero. If del y by del x is 0, this delta p will be also 0. Okay. That's why we consider the first boundary condition in this way, that at the open end, that is at x equal to 0, delta p is equal to 0. But you have seen that this delta p is equal to minus e times del y by del x. So this will be 0. It means since E is elasticity, that is bulk modulus of elasticity, which will be not 0, so definitely this del y by del x will be 0 at x equal to 0. This is actually our first boundary condition, okay, which will be used to find the constants A and B. Okay, this is our first boundary condition. Okay. Now let us think about the closed end. When you talk about the closed end of the tube, this is the place of zero movement or zero displacement of the particles of the gas. In other words, you can also say that this is the position where pressure variation will be maximum. At this closed end, pressure variation will be maximum and displacement will be 0. Okay. So you can write the second boundary condition in this manner, that this displacement y of xt is 0 when x is equal to L. Okay. In another manner, you can write it in this way, y of Lt equal to 0. It means y is 0 where x is equal to L. This is actually our second boundary condition. Actually, this second boundary condition will be used to find the normal modes frequencies, and this first boundary condition will be used to find the constant A. Okay. So now let us apply this first boundary condition, which I have mentioned here or here in this equation, which we have defined in here in equation number 6. So when you will apply the first boundary condition, that is delta P is equal to 0, okay, on equation 6, what will be your result? You can see when we will substitute x equal to 0 in every term which contains x in RHS, then actually delta P in LHS will be 0. So 0 is equal to k times E times B sine kx, but x is 0, so this will be sine 0, minus A cos kx. Again x is 0, so this is cos 0, and cosine of this much. But sine 0 is 0, so this first term inside the square bracket will be 0. Okay, cos 0 is 1. Okay. Now for all time this cosine function cannot be 0, and k and e both are not 0. So definitely you can say that this minus a is equal to 0, or you can also say that A is equal to 0. So applying the first boundary condition, we obtain the value of constant A, which we have we can see it is equal to 0. Okay. So now what will be the value of y when you have obtained the value of A? So for getting the value of y, now substitute A equal to 0 in the expression for y. You have seen earlier that y is given as A sin kx plus B cos kx times this much. But A is 0, so now B of xt can be given as B times cos kx times cosine of this much. Okay. Actually, you will see later on that this equation will be used to find the shapes of the different modes of vibration. Shapes of the vibrating air column in different modes of vibration. Okay. Now, as I have told you earlier, when you will apply the second boundary condition now on this equation 7, then you will get the normal mode frequencies. Okay. And for this, let us apply the second boundary condition. What is second boundary condition? We have seen that y of xt when x is equal to L, that is equal to 0. It means at the closed end, no particles of the gas will get displaced. Okay. So now put x equal to L in RHS of equation 7, and when you will put x equal to L according to this boundary condition, this y will be 0. So you can write now 0 equal to B times cos kl times cosine of omega t plus pi. Now again you know that this B is not 0 and this cosine function cannot be 0 at all time t. Although it may be 0 at a particular time, but for all t it cannot be 0. So it is obvious that this cosine of kl will be 0. Okay. And if cos kl is 0, what will be the general value of kl? The general value of kl, you know, this will be equal to n minus half times pi. N minus half times pi. Here n will be equal to 1, 2, 3. You can check. When you will consider n equal to 1, this will be pi by 2, and you know cos pi by 2 is 0. When you will take n equal to 2, this will be 3 pi by 2, and you know cos 3 pi by 2 is also 0. So these are the general values of kl. Now let us consider our air column is vibrating in nth mode. You have seen earlier that this constant k is given by omega over v. But as length of the tube is fixed, but n varies, it means k will have different value. For different value of n, corresponding to different value of n, k will have different value. So in this expression, if k will change, what in RHS will change? Definitely this omega, because v is actually a constant. Okay. So here I have written if n is equal to n, it means our air column is vibrating in nth mode, then the frequency, angular frequency of vibration is omega n. Okay. So that instead of k, I have written omega n over v. Okay. So our result is omega n over v times L equal to this much. Okay. And therefore you can easily find the value of this omega n, which will be n minus 1 over 2 times pi over L times v. But you have seen that this v is equal to a square root of e over rho. So omega n is equal to n minus 1 over 2 times pi over L times this much. Okay. This is actually the angular frequency of vibration of the air column, or you can say longitudinal vibration of the air column in its nth mode. Okay. Now if your aim is to find the frequency of vibration, that is the frequency which is measured in hertz, which is also called regular frequency. Omega n is already frequency, but you say it is angular frequency or circular frequency, okay? But nu n, which is a regular frequency, and it is measured in hertz, that is given as omega n over 2 pi. So when you will divide the RHS of equation 8 by the constant factor 2 pi, you will get this frequency nu n. And this nu n will be then what? This is n minus 1 over 2 over 12 times this much. So you can see how easily applying the second boundary condition we have obtained the expression for the normal mode frequencies. Okay. Now for finding the shape of the normal mode of vibration, we will have to find the value of y in a particular mode. So you have seen earlier that this y of xt is given as b times cosine of kx times this much. Now if we are talking about nth mode, then we will write this y as yn. Okay. And here there was k, and now k will be replaced by omega n over v. Okay, omega n over. But you can see from here that this omega n over v is equal to what? This is n minus 1 over 2 times pi over L. Okay. So instead of this omega n over v, I have written here n minus 1 over 2 times pi by L. Okay. So this is the expression for yn of xt, by the use of which we will get the shapes of the different mode vibration. Okay. Now let us analyze this result for particular values of n. Okay. You can see, since the expression for nu n and yn consists of n, so for different value of n, we will have different frequencies of vibration and different shapes of the mode. Okay. If you talk about the least frequency of vibration, in this case, that is the case when one end of the tube is closed and another is open. For finding the minimum frequency of vibration or least frequency of vibration, you can see this equation number 9. You have to take the least value of n. And what is the least value of n? The least value of n is equal to 1. Actually, when we will take n equal to 1, we will get the smallest frequency of vibration. And you know, that smallest frequency of vibration is also known as fundamental frequency. So for getting the value of fundamental frequency, let us put n equal to 1 in this equation 9. And then you can see the fundamental frequency nu1 will be equal to 1 over 4L times a square root of E over rho. This is the expression for the fundamental frequency or the least frequency or the minimum frequency of vibration of air column in a tube which is closed at one end and open at another end. Okay. Now for getting the shapes of this normal mode vibration, we will substitute n equal to 1 in this equation number 10. Okay. So you can see I have replaced everywhere this n by 1. So in LHS you will write y1 of xt. Okay. And that will be equal to b times cosine of pi x over 12, because here we will take n equal to 1 and 1 minus 1 over 2, that will be 1 over 2. So this is pi x over 12. Okay. Times this much. Cosine of omega 1t plus phi 1. Okay. Now see this equation. If you will take x equal to 0, then this cosine function will be cos 0, which is 1, and this 1 is the maximum value of this cosine function. So at x equal to 0, the value of this displacement y1 of xt will be maximum. This will be maximum. So when you will write y1 in this direction, this will be maximum. One thing you must remember, although I have shown in this figure y1 in vertical direction, but y1, you know, this is the longitudinal displacement. In accordance with figure, I have written this in vertical direction. Okay. So at x equal to 0, I have written here, you can see this cosine function will be 1, that is maximum, and so y1 at x equal to 0 is maximum. Okay. Actually, the point of maximum displacement is also called antinode. So an antinode is formed at the open end of this tube. Okay. Now you can see, when we take x equal to L, then what will be this cosine function? This will be cos pi x over, this is cos pi x over 2L, but x is L, so pi x over 2L. If x is L, this will be pi L over 2L. L will cancel out, and so this will be pi by 2. So this cos pi x over 2L will be cos pi by 2, which is equal to 0. And if this cosine function will be 0, y1 will be 0. It means displacement of the particle at the point x equal to L, which is actually the closed end of this tube. At that point, displacement is 0. And the point where displacement of the particle is 0 at all time, permanently it is at its 0 value. That is called node. So in this case, there is an antinode at the open end and a node at the closed end. Now you can see, between x equal to 0 and x equal to L, this y1 of xt is not 0 at any point. So there is no node between this x equal to 0 and x equal to L. That's why if you want to draw the shape of this mode, that will be just like as I have shown in this figure. This is just a graphical plot of y1 in against of x. Okay, in against of x. So I think we have clearly understand how we can obtain the fundamental frequency and the shape of the mode in this case. Okay. Now let us consider the second higher frequency. For this you have to take n equal to 2. And when you will take n equal to 2, see this equation number 9. Let us put 2 here at the place of n, and when you will put n equal to 2, your result will be nu2 equal to 3 over 4L times this much. But you know, 1 over 4L times a square root of E over rho, that is nu1. So this nu2 is simply equal to 3 nu1. So this first overtone is 3 times of the fundamental frequency. 3 times, okay? Or you can say that this is an odd multiple of fundamental frequency, okay? Now, what will be the shape of the mode? For that, you have to again see this equation number 10, which actually determines the shape of the mode. And for this, you have to put n equal to 2 in this equation 10. So when we will substitute n equal to 2 in that equation, our expression will be y2 of xt equal to b times cosine of 3 pi x over 12 times this much. Okay. Now again see, what will be this y2 when x is 0? When x is 0, then this cosine function will be cos 0, and cos 0 is 1, which is maximum. So again at x equal to 0, the displacement y2 will be maximum. And when you will take x equal to L by 3, then you will see that the argument of cosine function, that is this 3 pi x by 2L, this will be pi by 2. And therefore, y2 will be 0. And again this y2 is 0 at x equal to L. So in this case, actually between x equal to 0 and x equal to L, y2 is 0 at two positions. First position is x equal to L by 3 and another is x equal to L. So the shape of the mode in this case will be just like this, which I have shown in this figure. And you can also say that this is the graphical plot of this y2 in against of x. Okay. Now you can see at this position at the open end, the displacement is maximum. So this is the point of antinode. So I have marked it by A1. Here also I have marked A2, which is the position of antinode, and N1, which I have marked here, where the displacement is 0, that is node, and N2 is also a node. So in this case, you can see there are two nodes and two antinodes in this vibration. Okay. Actually, when you will try to find the higher harmonics, you will see that in this vibration, the frequencies are nu 1, 3 nu 1, okay, 5 nu 1, 7 nu 1, and so on. Actually, the frequencies like 2 nu 1, 4 nu 1, 6 nu 1 are absent. They are not present. So you can say that when the tube is closed at one end and open at another end, then it has only odd harmonics of frequencies 3, 5, 7 times of the fundamental frequency. And all the even harmonics of frequency like 2 nu 1, 4 nu 1, 6 nu 1, 8 nu 1, and so on are absent. Okay. So in this way, how easily we can obtain the frequencies of vibration of the air column contained in a tube whose one end is closed. You can see how easily we can obtain it. Okay. And I think definitely you have clearly understand all the calculations. Okay. Now we are going to see the same problem when the tube is open at both of its ends. Actually, when we will study the sound wave, in that case we will call it open organ pipe. Okay. Actually, same mathematics will be done here. Okay, but that will be just identical as you have seen earlier. So I have actually sorted this calculation, and this is just a homework for you. You can try it and solve all the equations like just like we have solved earlier, and then you will see how these results are obtained. So I have not made here the each and every aspect of the calculation. As you have seen earlier that in this case the tube is open at both ends, and you have seen earlier that at the open end the displacement of the particle is maximum. Okay, and there is no pressure variation, that is delta P is equal to 0, or the strain experienced by the particle at the open end is 0. And since both ends, that is at x equal to 0 and x equal to L, this tube is open. So in this condition, what will be the boundary condition? The boundary condition will be delta P at x equal to 0, which is actually the pressure variation, and at the open end there is no pressure variation. So this delta P at x equal to 0 is 0. But when delta P will be 0, you know, strain del y by del x will be also 0. Okay. So you may write the first boundary condition in this way. Again, at x equal to L, the tube is open. Again the same condition will hold. So this delta P is again 0 at x equal to L. Or you can say that del y by del x is 0 at x equal to L. Okay. Now, when you will impose this first boundary condition, that is delta P equal to 0 at x equal to 0 on the previous equation I have shown here, that is on equation number 6, then you will see that this is your equation 6. You can see here, this is equation 6. When you will take this delta P equal to 0 at x equal to 0, this is the just previous problem. So you will take x equal to 0 in RHS and delta P equal to 0 in LHS, and after solving you have seen just earlier that we have the 0 value of the constant A from this boundary condition. Okay, so in this condition we will have A equal to 0. Okay, and when A is 0, then when you will substitute this A in the defining equation for y, okay, and again you can see this delta P is 0 at x equal to L. So in this condition, the second boundary condition you will have like this: sin KL equal to 0. I have not done all the algebra, as I have told you earlier that you can do it. Okay, and sin KL is 0, then what is the general value of KL? You know, if sin theta is 0, the general value of theta will be n pi, and therefore KL will be equal to n pi. Here again we will take n equal to 1, 2, 3 and so on. One can think that if sin theta is 0, then theta is equal to n pi, and mathematically n may be 0, 1, 2, 3 and so on. But here I have not taken n equal to 0, because when you will take n equal to 0, then displacement everywhere will be 0, which is unphysical. So in this physical problem, n equal to 0 is restricted. The least value of n you may take 1. Actually, this fact I have already explained earlier too. Okay, you can remember. Again, you know, if we are talking about the nth mode vibration, then instead of k we will write omega n over v. So omega n over v times L will be n pi, and therefore omega n is equal to n pi over L times v. Again, let us substitute the value of v, which is a square root of E over rho. So in this way we have obtained the angular frequency of nth mode of vibration, and therefore the regular frequency measured in hertz nu n is given as omega n over 2 pi, and that will be equal to this much. This is n over 12 times this much. Okay, this is just identical to the frequency of a string, vibrating a string, which is clamped at both of its ends. This is just identical to that. Now, in this way, we can obtain the different frequencies of vibration by substituting the different value of n. So when you will take n equal to 1, the least frequency, which is also called fundamental frequency in this case, will be 1 over 12 times this much. And you can see this frequency is just 2 times of the fundamental frequency of the closed organ pipe. So in case of open organ pipe, the fundamental frequency is 2 times of the fundamental frequency of closed organ pipe. You have seen in case of closed organ pipe, nu1 was 1 over 4L times this much. But in this case, at the place of number 4, there is 2. So this is 2 times of that frequency. Okay, and this nu2 will be equal to 2 over 12 times this much, which is 2 nu1. Nu3 will be 3 nu1 and so on. So what you find here, actually in this case you can see, if you are talking about a tube which is open at both of its ends, then its vibration consists of all the harmonics, both even and odd harmonics of the fundamental frequency. Okay, this is the basic difference. Okay, so you can notice that all even and odd harmonics are present here, and as I have told you earlier that when uh, the positions where the particle displacement are maximum are called antinodes, and the positions of the particles where the particles are permanently at rest are called nodes. So in this case, what will be the number of nodes and antinodes, and what will be the shape of the different mode? I have shown actually two modes here for n equal to 1 and n equal to 2. You can see in this case, actually at both of the ends there will be antinode, okay, and in the just mid there will be node, okay. But when n is equal to 2, then there are how many nodes? There are actually two nodes, okay, two nodes, and two antinodes, three antinodes, sorry, three antinodes, A1, A2, and A3. These correspond to antinode, and N1 and 2 correspond to nodes in this second figure. So in this case, number of antinode is greater than number of nodes by 1. Okay, number of antinodes minus number of nodes, that will be equal to 1. But in previous case we have seen the number of nodes and number of antinodes was equal. Okay, so in this way we have finished the problem of the vibration, longitudinal vibration you may say, of air column. Okay, when the boundary conditions are that the tube is closed at one end and the tube is open at both ends. Okay, so in this way we have seen three important examples for the study of normal modes of continuous system, and I think definitely this series of lecture will be very helpful for you for your examination purpose. Okay, thank you very much.